Hello everyone, thank you for joining us today. We are Group 13 from the course Deep Learning and its Applications at IIT Mandi, and I am Prisha. Now we are going to walk you through this fascinating paper that addresses a significant challenge in the world of medical imaging. This paper is titled CoBooM, Codebook Guided Bootstrapping for Medical Image Representation Learning. Now this work is authored by Azad Singh and Deepak Mishra from IIT Jodhpur. Today we will be walking you through why existing methods don't work well in medical imaging and what makes CoBooM different and how it addresses key challenges in this space. I will begin by setting the context with the motivation and the problem statement before my teammates take over for the methodology and the experimental analysis. Now, let's start with a simple question. Why not just use supervised learning? Well, in medical imaging, labeling is extremely expensive and time consuming. Unlike labeling dogs or cats on Instagram photos, you need a trained radiologist to annotate a chest X-ray. A mistake here can be a matter of life and death. Now imagine building a model to detect diabetic retinopathy. You would need thousands of expert labeled fundus images. But in many parts of the world, even getting that many unlabeled medical images is a challenge, let alone annotated ones. That is precisely where self-supervised learning shines. Learning patterns and structure from raw and labeled data. It has been a game changer in natural images. Frameworks like SIIM-ACR, BYOL and MoCo have set new standards. But medical images, they are a different beast. So here is where the problem starts. These popular SSL methods rely heavily on creating positive and negative pairs of images. So think of this like trying to teach a model the difference between twins. In natural images, this works well. A car and a dog look different enough, but in medical images, two different X-rays can look nearly identical, and yet one might have a tumor while the other doesn't. So what goes wrong? Firstly, medical images are highly similar anatomically. Let's take an example. Imagine you have hundreds of chest X-rays from different patients. Now while each one is technically different, visually they might look almost the same. The rib cages, the lungs, the heart outline, they'll follow a standard layout. So even though the disease may be present in one and absent in another, it is extremely hard for SSL algorithms to detect those subtle differences when most of the image looks the same. Now contrast that with natural images. In a dataset like ImageNet, a dog looks very different from a car or a tree. So positive and negative pairs in contrastive learning are easy to define. But in medical images, it's not that clear cut. Secondly, the idea of positive and negative pair, which is core to many SSL methods, becomes tricky. In SIIM-ACR, for example, we take two augmentations of the same image as a positive pair, and any other image in the batch is considered a negative. But in medical dataset, this logic breaks down. Two chest X-rays from different patients might be almost identical in structure, yet they are treated as negatives. Or two retinal images from the same eye taken at different times may contain tiny variations that matter clinically, but they are treated as positives after augmentation. This mismatch confuses the model, leading it to representations that are either too generic or they fail to capture important disease cues. This causes model to learn superficial or even misleading features. You might end up with a model that is good at spotting rib patterns but blind to actual disease makers. Now let's take a real world example to show why this is more than just a theoretical problem. So imagine a rural healthcare setup, say a small diagnostic center in a remote area, using an AI model trained with contrastive self-supervised learning to detect tuberculosis from chest x-rays. The model during table, uh, it saw a lot of similar looking lungs during its training, right? And learned to treat visual similarity as clinical similarity. Now, let's say a patient comes in with an early stage TB infection. The infection is subtle, perhaps just a tiny lesion, and the X ray looks almost identical to a normal one. The model, based on its contrastive learning, assumes this looks like the healthy lungs I've seen before, though no diseases here. This kind of mistake isn't just bad accuracy, it's diagnostically dangerous. The disease might go unnoticed, untreated, and could progress into something life threatening. These are the real risks of applying generic SSL models to sensitive domains like medicine. We are not just losing a few accuracy points, we could be losing lives. So, the fundamental problem becomes this: how can we train models that understand the visual world of medical images with all its recurring anatomical structures, but without letting the similarity of structure override the importance of disease specific variation? In natural images, positive and negative samples are easy to construct. A picture of dog versus a picture of a bicycle. But in medical images, things are much more subtle. For example, take two retinal images. One has mild diabetic retinopathy, the other has early signs of glaucoma. To the human eye, even to a non specialist doctor, they might look nearly the same. So, relying on traditional SSL ideas like augment this image and compare it to others, it misses the medical context. Now, what do we need? We need models that can, firstly, recognize repeated visual motifs across different images like optic nerves, lung lobes, or cardiac silhouettes, and isolate small meaningful changes like a nodule, a hemorrhage, or a lesion. That's a very specific and challenging type of representation learning, and that is what motivates the design of CoBooM. So, how does CoBooM solve this? At a high level, it uses a hybrid architecture, a mix of discrete and continuous representations. Here is the core idea. Imagine building a visual vocabulary, a kind of code book that can learn to recognize common anatomical parts like a patch for lungs or a patch for retina veins. These visual parts are quantized. Think of them as entries in a dictionary. Then instead of just learning everything through one encoder, CoBooM uses two pathways. One encoder learns traditional continuous features and the other encoder passes patches through a vector quantizer, mapping them to discrete codebook entries. Now these two streams are then fused using a novel attention mechanism, allowing the model to ask which parts of this image are familiar and can be reused from the codebook, and which parts are new or different and need to be represented freshly. With that, I will hand it over to the next speaker, Arithro, with whom we will explore the architecture that enables this, including two encoders, a quantizer, and a clever attention mechanism that bridges the two worlds. Thank you.
Hello everyone. In this part of the presentation, I'll be diving into the key idea behind KoBoom, its high-level framework, and breaking down the main components that make this method both unique and effective in handling medical image representations. Key idea integrating continuous and discrete representations. Let's start with the central idea. KaBoom stands for Codebook Guided Bootstrap Model, and at its heart, it's a self supervised learning SSL framework specifically designed for medical images. Now, why is this necessary? Well, medical images have two distinctive challenges. They often require fine-grained details for tasks like segmentation or anomaly detection. At the same time, they exhibit recurring anatomical structures. Think of common visual patterns like vertebrae in a spinal scan or blood vessels in a retinal image. Kaboom elegantly addresses both needs by combining continuous representations, which are embeddings generated from CNN-based encoders capturing subtle and local variations in image details, and discrete representations, which are essentially compressed visual patterns stored in a codebook, acting like a dictionary of recurring anatomical features. By learning both jointly, Kaboom achieves a richer and more semantically meaningful embedding space for medical images compared to conventional SSL approaches. High-level framework. So how does Kaboom achieve this? Let's look at its high-level framework. At a glance, the architecture is composed of four main components: two encoder, a context encoder denoted as f theta, and a target encoder denoted as f of phi. This processes different augmented views of the same image. A quantizer model with a codebook which takes continuous embeddings and assigns them to discrete code words. A DiversiFuse module which uses multi-head cross-attention to fuse information between continuous and discrete spaces effectively. An optional decoder for reconstruction purposes, allowing the model to regenerate images and ensure the representation preserve essential structural details. This overall framework is visualized in Figure 1 of the paper. Now let's unpack each of these components one by one. Two encoders F theta, context encoder, and target encoder F of phi. These two encoders lie at the foundation of CoBoom's design. They follow a momentum contrastive learning paradigm inspired by frameworks like MuCo. The text encoder f of theta processes one augmented view of a medical image. The target encoder f of phi processes a differently augmented image view of the same image. The target encoder parameters are momentum updated versions of the context encoder's parameters, ensuring stability in representation learning. The encoders generate continuous embedding denoted as Z1 and Z2, representing the images in a high-dimensional little space. Quantizer model with codebook. Now, continuous embeddings alone often lack interpretability and may miss recurring visual patterns vital in medical images. To address this, Kaboom introduces a quantizer module. This module uses a codebook, essentially a learned dictionary of visual patterns or code words. Here's how it works. The continuous embedding Z1 from the context encoder is passed to the quantizer. The quantizer assigns each vector in Z1 to its nearest code word in the codebook. This process converts continuous representation into discrete representations. Think of it like taking a rich continuous image representation and tagging each part of it with the closest known visual pattern, making it both efficient and semantically meaningful. DiversiFuse model, multi-head cross-attention. Now that we have both continuous embeddings from the encoders and discrete representation from the quantizer, we need an effective way to fuse them. This is where the DiversiFuse module comes in. It's a multi-head cross-attention mechanism to fuse the continuous features from the encoders and the discrete code words representation from the codebook. This allows the model to attend selectively to both fine image details and higher level anatomical structures simultaneously. By doing this fusion across multiple attention heads, Kaboom captures diverse contextual relationships within medical images, hence the name DiversiFuse. Optional decoder. Finally, an optional decoder can be appended to the fused representation for image reconstruction. Why is this important? It serves as an auxiliary self-supervision objective, ensures that the combined embeddings retain essential structural details, provides a way to measure reconstruction error, acting as an indirect regulation. In practice, this helps Kaboom learn structurally faithful representation without relying on labeled data. So, to quickly recap, Continuous representations capture fine details. Discrete representations capture recurring patterns via codebook. Two encoders process augmented image views. A quantizer converts continuous embeddings to discrete code words. DiversiFuse uses multi-head cross-attention to fuse both spaces, and an optional decoder reconstructs image for auxiliary supervision. All of these components work together to create a robust and semantically aware SSL framework for medical imaging. That wraps up the high-level framework and components of CoBooM. In the next segment, we will explore how this architecture performs compared to existing methods and the kind of performance gains it achieves in various medical image tasks.
Let's now take a deeper look at the core components that make CoBooM unique: the quantizer module and the DiversiFuse submodule. Starting with the quantizer, this module is responsible for discretizing the feature maps produced by the target encoder. So instead of just relying on continuous high dimensional embeddings from CNN, we introduce a codebook, essentially a learned dictionary of visual patterns. Now, this codebook contains k discrete code words, each representing a distinct anatomical or visual pattern frequently seen in medical images. Like think of lung outlines, rib structures, or cardiac uh, figures. Now, during training, for every spatial location feature map, we find the closest matching code word from the code book based on Euclidean distance. Now, this gives us the discretized or quantized version of the image representation. To train this quantizer, we use what's called a vector quantization loss. It's made up of two parts. First is the codebook loss, and second is the commitment loss. Now, the codebook loss is something that encourages the code words to move closer to the encoded features, and committed loss is something that is pushing the features to commit to their nearest code word, reducing redundancy eventually. Mathematically, the equations, the quantizing loss is defined as LQ equals to LCB plus alpha times LCE, where LCB is the squared distance between the features and its assigned code word with stop gradient applied. LC is the commitment cost, the squared distance from code word back to the feature, and alpha is the balancing weight. This dual objective helps the code book evolve dynamically during training and ensures that the discrete features stay meaningful. Now let's move on to the second key innovation, the DiversiFuse submodule. So once we have both continuous features from context encoder and discrete codebook features from the quantizer, we need to combine them in a meaningful way. That's where DiversiFuse comes in. It uses a multi-head cross-attention mechanism, somewhat inspired by transformers. Like here is how it works. The discrete representations act as the queries. The continuous representations are keys and values. Now, through cross attention, each discrete token attends to relevant continuous tokens, allowing for richer context aware fusion. The attention score is computed using a dot product between the discrete query and the continuous query. That is, SS score is equals to QD dot KCT. Then we apply a softmax to get the attention weights and use those to aggregate values from continuous representations. This process is repeated across multiple attention heads. Each head captures different aspects of or scales of interactions between the discrete and the continuous features. Finally, the output of all heads are concatenated to get the fused embedding. The beauty of this setup is that it allows the discrete representations to guide the model's focus. They essentially highlight the recurring anatomical structure while the continuous features contribute the fine details. So the result is a hybrid embedding, rich in semantic meaning, and grounded in both anatomical consistency and pixel level details. The fusion is what sets CoBooM apart from earlier SSL methods that rely purely on one type of representation. Now, this concludes the core and architectural innovation behind CoBooM. Now, up next, we'll look at how these components come together during training and what loss function guide their learning. Aksha will take this part.
Let's begin with the loss function used in CoBooM. The goal of the loss is to guide the model in learning useful representations by leveraging both continuous and discrete features. There are four key components that make up the total loss. First, we have two similarity losses, denoted as L1 and L2. These are based on cosine similarity. L1 compares the global feature embeddings produced by the context encoder and the target encoder, which are applied to two differently augmented versions of the same input image. This helps ensure consistency between the two views. L2, on the other hand, compares the context encoder's output with the fused representation that combines both the continuous features from the encoder and the discrete features from the codebook. This encourages the model to maintain alignment not just within the continuous representations, but also between the continuous and discretized representations. The next part is the quantization loss, LQ. This part is crucial because it ensures that the model learns meaningful discrete representations. The quantizer module takes the feature map from the target encoder and maps it to the nearest code word from a learned codebook. The loss is composed of two terms: the codebook loss, which pulls the code words closer to the encoder's output using a stop gradient operation, and the commitment loss, which ensures that the encoder commits to using specific code words and doesn't drift away too far. These two together promote stability and consistency in the discrete representations. In addition to that, there is also a reconstruction loss, LR. This is a simple L2 loss between the original image and a reconstructed version that is generated by a decoder. This helps the model preserve fine-grained image details and spatial context, which is especially important for segmentation tasks. The decoder takes the fused output of the DiversiFuse model, which integrates discrete and continuous features through cross-attention and reconstructs the input image. By doing this, the model is forced to retain both global semantics and local textures. All of these components are combined into the final loss function. L is equal to alpha L1 plus L2 plus LQ plus gamma LR, where both alpha and gamma are set to 0.5. These hyperparameters balance the trade-off between alignment, quantization, and reconstruction. A symmetric version of this loss is also used, where the roles of context and target encoders are swapped during training, further stabilizing learning. Moving on to the datasets. CoBooM is evaluated on a wide range of medical imaging datasets, which help assess its generalization ability across tasks and modalities. For pre-training, it uses the NIH ChestX-ray14 dataset, which includes over 86,000 frontal view chest X-rays with high anatomical similarity, making it ideal for studying representation learning. Alongside that, EyePACS is used for pre-training on retinal fundus images, offering around 35,000 samples. These two datasets represent very different modalities, helping test the flexibility of the framework. For downstream classification tasks, three datasets are used: the official NIH test set, which has around 25,000 images, MuReD, which provides over 2,000 fundus images, and ODIR, with 7,000 fundus images. For both MuReD and ODIR, 20% of the samples are held out for testing. For segmentation, the SIIM-ACR pneumothorax dataset is used, which contains over 12,000 X-rays labeled for the presence or absence of pneumothorax. The dataset is carefully balanced between positive and negative samples, and 20% is set aside for validation. To simulate low resource settings, experiments are conducted with various labeled data splits: 1%, 5%, 10%, 30%, and 100%. This helps demonstrate how well CoBooM performs under limited supervision, Interestingly, results show that even with just 1% label data, CoBooM outperforms several strong self-supervised learning baselines, indicating that it extracts high-quality features during pre-training. Now let's look at the implementation details. CoBooM is implemented in PyTorch and trained using an NVIDIA RTX A6000 GPU. The architecture uses ResNet 18 as the backbone for both the context and target encoders. This makes the model relatively lightweight and fast to train, while still powerful enough for feature extraction. The input images are resized to 224 by 224 pixels, with a batch size of 64, and training is done over 300 epochs. The codebook used in the quantizer has 1024 vectors, each of 512 dimensions. This provides a rich but manageable vocabulary of visual patterns. To transform features, both the context and target encoders are followed by 3-layer MLP projection and prediction heads, each outputting 256-dimensional embeddings. These help in projecting high-dimensional feature maps onto a compact and comparable space for loss computation. For optimization, the model uses the Lars optimizer with a base learning ratio of 0.02. A cosine decay learning rate scheduler is applied without restarts. The gradual learning rate reduction helps the model converge smoothly. The DiversiFuse module, which is embedded within the quantizer, uses multi-head cross-attention to fuse continuous and discrete features, enhancing the model's ability to capture both global semantics and localized patterns. One key insight from the implementation and ablation studies is that CoBooM achieves strong performance even without fine-tuning the encoder. The difference in performance between linear probing and semi-supervised fine-tuning is very small, especially for low-labeled data scenarios. This is quite significant as it suggests the model learns highly transferable and robust features during pre-training, something that's particularly valuable in real-world medical settings where labeled data is scarce and expensive to obtain.
The authors conducted a comprehensive evaluation of their proposed method, CoBooM, by comparing its performance with several state-of-the-art self-supervised learning baselines. These baselines included SIIM-ACR, BYOL, VicReg, CADE, PCRL-V2, and DIRA. Linear probing evaluation, which is Table 1. When assessed using the linear probing protocol, CoBooM consistently outperformed all the aforementioned SSL baselines across multiple medical imaging datasets. Specifically, CoBooM achieved an average increase of 3% in AUC, which is area under the curve, scores on 3 widely used datasets: NIH ChestX-ray14, ODIR, which is ocular disease intelligent recognition, and MuReD, which is multi-resolution diabetic retinopathy. This demonstrates the model's superior ability to extract meaningful and transferable representations from unlabeled data for downstream classification tasks. In terms of segmentation performance, CoBooM achieved a dice coefficient of 57.5 on pneumothorax segmentation tasks, which marks the highest score among the evaluated methods. This indicates its strong capacity for learning spatial coherent and diagnostically relevant features. Semi-supervised fine-tuning results, referring to Table 2. The study also evaluated CoBoom's performance in a semi-supervised learning scenario where only a small percentage of labeled data is available for fine-tuning. Across all levels of label availability, CoBooM maintained a clear advantage over competing methods, notably at the extremely low level of supervision of just 1% labeled data. CoBooM achieved an impressive AUC score of 65.8%, outperforming the best performing baselines by a margin of 2 to 3%. Moreover, CoBooM required minimal fine-tuning efforts to adapt its pre-trained features to various downstream tasks, underscoring its effectiveness and efficiency in low resource settings. Diagnostic capability, interpretability, referring to Table 2. To further illustrate the practical utility of CoBooM in medical diagnostics, the author presented diagnostic heat maps that visualize models' attention across different pathologies. These maps revealed that CoBooM was significantly more effective at localizing pathological regions compared to SSL methods, the other SSL methods. The improvement was particularly evident for clinically important conditions such as atelectasis, pleural effusion, cardiomegaly, and pulmonary masses. This enhanced localization suggests that CoBooM learns more semantically meaningful and anatomically aligned representations. Ablation studies. To better understand the contribution of various components within the CoBooM framework, the authors conducted a series of ablation experiments. When the DiversiFuse module was removed, the model's performance experienced a noticeable decline of 2%, demonstrating the importance of feature diversity introduced by this component. Additionally, it was observed that decoder components specifically contributed to improvements in segmentation tasks, helping the model generate more accurate spatial predictions. However, for classification tasks, the inclusion of the decoder had no significant impact, indicating a degree of task specific utility within the architecture.
Hello everyone. To conclude our discussion on CoBooM, I'll now walk you through the key takeaways, important insights, and possible future directions of this work. The authors propose a novel, self-supervised learning framework that integrates discrete and continuous representations of medical images. This is done using a codebook and a special module called DiversiFuse, which together help the model capture both fine details and broader structural patterns. The result is a representation learning approach that is not only effective but also highly data efficient, meaning it performs well even with very limited label data, which is a critical advantage in the medical domain where annotation is time consuming and expensive. What's remarkable is that CoBooM doesn't need extensive fine tuning. It performs very well even when only a small percentage of label data is used for training. So what did the results actually show? Across multiple datasets, including NIH chest X-rays, fundus images from MuReD and ODIR, and the SIIM pneumothorax dataset, CoBooM consistently outperforms state-of-the-art SSL methods like SIIM-ACR, BYOL, and PCRL-V2. For instance, with just 1% of label data on the NIH dataset, CoBooM achieved an AUC of 65.1%, outperforming the best baseline by over 3 percentage points. That's a significant jump in performance, especially at such a low data regime. Also, during segmentation tasks, the model reached the highest DICE score of 59.6%, which is again above all baselines. Another major insight is about fine-tuning efficiency. While most SSL methods showed large improvements from linear probing to fine-tuning, CoBoom's performance remained consistently strong even without fine-tuning. That tells us that the pre-trained representations are already highly transferable and meaningful, a strong sign of good generalization. And finally, the DiversiFuse module turned out to be crucial. When it was removed, performance dropped by 2% across tasks. This proves that combining discrete and continuous features helps the model focus on important anatomical patterns that may otherwise be overlooked. Now, where can this work go from here? First, the authors mention that extending CoBooM to other imaging modalities like MRI or CT scans could be highly beneficial. These modalities have different spatial characteristics and might benefit even more from the hybrid feature approach. Second, An exciting direction would be to explore adaptive or learnable codebooks, rather than using fixed code word sets. This could help the model better align with different types of medical data or even patient-specific variations. Third, CoBooM is well positioned for low-resource clinical environments such as rural hospitals or developing countries, where label data is extremely scarce. Optimizing the framework for real-world deployment, especially with smaller or portable models, could have a significant impact on accessibility to medical AI. Another avenue is to improve model interpretability. Since the codebook can capture discrete semantic features, future work could aim to map these code words to known anatomical regions or pathologies, making the model's decisions more explainable to clinicians. So, to summarize, CoBooM offers a powerful and generalizable approach to medical image representation learning by combining the best of both continuous and discrete embeddings. It achieves strong performance with minimal supervision and shows promising adaptability for future clinical and research applications. Thank you.